recording. Okay, so as I understood, we have 4 more lectures, and the plan more or less the following. So we today and the next week, the plan is to obtain some closed formula for generating series which we obtained last time. So this z function which we had last time, but so generating series for, say, generalized double Hurwitz numbers, and this for today and for the next week. And then for the last 2 lectures, we hope that we will prove in the last 2 lectures topological recursion, at least part of present part of the proof of topological recursion again to all of these cases immediately, so in one time. Okay, so it's a general plan, and today we start with this function z that we obtained last time. So last time we were on iDraw. Today I'm here. So, but you have lecture notes in the Google Drive. So I just repeat the formula. So we stopped. Piotr Igorich stopped last time on this expression. So we had this z, which is sum over all lambda, which are partitions. So model lambda, we usually write like sum over n, sum over all model lambda is equal to n, e to the power sum of all. How do we write usually? From lambda psi of h j minus I s lambda of p, p1, p2, etc. s lambda of q1 over h, q2 over h, etc. And so, okay, do you remember this formula or not? So, do you hear me? Do you remember something like that, or absolutely no, and I should repeat something? Piotr Igorich.
I think we remember.
Okay. Could you please cut lecture notes for the lecture 11, 10, 9. Yeah, please. Yeah, okay. Так, Alexei wrote. Okay, so we have this formula, and yes, for we obtain numbers when we take some specific, if we specify this psi function, and somehow specify this sequence q1, q2, etc. For example, q1 is equal to 1 and all other q's are equal to 0, and if psi just equal to so psi of x is equal to x, then we obtain just simple Hurwitz numbers, and then in other specialization, we obtain other types of Hurwitz numbers. Okay, so Alexei is trying to connect to us. Okay, so,
I hear you. Do you hear me?
Что?
Can you hear me? Can you hear me well?
Да, мы вас слышим, да.
Okay, so.
Okay, and so today we obtain some. I hope that we obtain a formula over as a summation over some simple graphs for more or less for this function z. Okay, so to do this, let me define some operators in the Fock space. So we already have this space of infinite power series in variables p1, p2, etc. So say operators in the Fock space. We have this, I hope, this F calligraphic F, capital F space. It's space of infinite power series, vector space of infinite power series. And I will use the following notation. This is the notation, and it calls a vacuum vector. Vacuum vector, and it means one. It is one in this space F, calligraphic F, and also one more notation. This symbol is it calls co-vacuum vector, and it is it means the following. It means the taking the free term in the power series from F. So it means taking free term of, say, F from F calligraphic. So if we have when we have a formal power series in p variables, we could and if I write something like this expression, it means that I take free term of F. It's just a notation. For us, it's just a notation. And I want to define operators in this Fock space. So, and okay, we already know a bit about these operators in the Fock space because of on the last seminar we prove the commutation relations for the operator J capital. So when you know already who are J's, so JM for m greater than 0 is m. Okay, let me write m d over dpm if m greater than 0, and p minus m if m less than 0, and 0 if m is equal to 0. This means that it is an operator. So let me write. It is if m greater than 0, it is a differential operator. If m less than 0, then it's an operator of multiplying by p minus m. Operator of multiplying by p minus m, and it's 0 if m is equal to 0. And so you know how to compute, how they compute. Okay, so like jk jl is equal to k delta k plus l0, and you know how to compute exponent of j's, yes? From the seminar problem, let me write exactly. If we have an exponent there, it's something like, yes, if we have this, then you know how to compute. See seminar. Okay, so we have these J operators, and also we have one more operator. Okay, and then okay, so in fact, I'll skip. So I'm skipping a lot now because of I do not introduce this dual. So there is this. Maybe you heard something about this boson fermion correspondence again, and I'm skipping now a big part of this picture from the fermionic point of view, and but if you are interested in, there is a nice and very beautiful theory book due to Mivo, Jimbo, and Data, where this theory is properly introduced and developed. But okay, one more operator which I want to define is the following guys. So E are the so-called one more definition. So I want to define this through the following formula. I want to define operators E. So okay, let me write the formula. And it's again definition. So all these are definitions, yes? So this is definitions of vacuum and vacuum vector. This is a definition of J, and it's again a definition. So maybe definitions. Through the following huge and strange formula. So let me write it, and then I will try to explain something. So through these, so you see here in the left hand side, you can think about it as a generating function for this EKL hat, guys, and I want to define now this EKL hat through the right hand side. And in the right hand side, we have in the right hand side you see x pi over I d yes over x minus y and minus 1 here. So it's a global minus 1. So okay, and in the right hand side we have this some combination of say j with pluses and j with minuses, so operators of multiplying by pi's and differential operators, this d over dpi, and the meaning of this formula is follows, that you can take a coefficient in front of the monomial in the right hand side. You can take a coefficient in front of the monomial of p variables and so in front of the monomials of multiplying by p variables and the differential parts, differential operators. So say in front of the monomial p in some power, and then d over dp, say n1, etc. And it is a polynomial. So this x, it is a polynomial. So it's a polynomial in x to the power 1 over half, and times and the y to the power 1 over half. Because of this this x minus y in the denominator, it's a geometric progression, in fact. Okay. And so then it is a polynomial in x to the power 1 over half and y to the power 1 over half. And this EKL hat is some combination of p and d per dp operators, which is equal to the coefficient in this polynomial in front of the x to the power l and times y to the power minus k. Okay, let me maybe write it down. So again, the meaning is follows. So first, take coefficient in front of the monomial like this. And then it is a polynomial. It is a polynomial in x to the power 1 half and y to the power 1 half. And then EKL hat is a coefficient in this polynomial, in front of x to the power k, y to the power minus l. So it is in the end, it is some combination of p, linear combination of monomials in p and d over dp variables. So it's some operator in this again in this Fock space. So I again skip, and it's a definition. Yes, it's a definition of this E operator. It is a bit not. So it is true, but I skip the maybe real and more natural and more explicit definition and description of this EKL hat in term in the fermionic space, and also it is a description as a of this EKL hat as some infinite matrices, but I want to skip this part at all and use this. And usually, if you have like a proper plenty of time, then you define this EKL hat some different way, and then prove this huge formula. But now I just define this EKL, the action of this EKL hat through this formula. So, and I want to use them in order to define one more guy, which is one more definition. I want to define some combination of this E capital hat operators. D of H is equal to exp of this sum WK EKK hat, where WK plus 1/2 minus WK minus 1/2 is equal to psi of HK. So yes, and let me write L. WL L L integer here. Okay. So does anyone understand anything or any questions, or you completely lost already? So what I will do. So any questions or comments or?
Can you recall what is psi?
Psi. Who is psi? Psi is this psi.
Mm-hmm.
So psi, how we define it? Yeah. So psi here is again as we defined it on the previous lecture. So say psi of some variable theta is any formal power series, in fact. Ck theta k, yes, any formal power series. Series. And then in the case of, say, simple Hurwitz numbers, again, this psi example for simple Hurwitz numbers, psi of theta is equal to theta. Okay, so what we will use later, we will use all, in fact, all these definitions. Yes, so we have this vacuum and covacuum, and we have this J, and in fact, we have this formula for E hat, and we construct. I construct from this EKL this operator D, and let me write one more statement about this D. The theorem.
Sorry. I have a question. How do we define this W? So we know only their differences?
Yes. So we know there through this. Yeah, we know their difference.
So they are defined after
Yes.
constant.
Yeah. In fact, really, they are defined up to some common additive constant, but in fact, this constant is not important, and so yeah.
Sum over of
Okay.
A with the coefficients 1, it kills the function.
Yeah. So we should, in fact, you should deal with this constant, but it, for our formulas, it happens that it doesn't important. Okay, yes, and theorem without proof. That we know. So now you see we define this D, curly D, this as some combination of these E operators, and these E operators we define through this huge formula as some combinations of Pi's and D over dPi's, and therefore we should have some formula for this D curly D operator as some operator in P and D over dPi, Pi and D over dPi, and it happens that this D operator has very nice expression, and in fact this D, so it is possible to understand how this D acts on Schur function. So D acts on Schur function as lambda as it's a diagonal operator in the basis of Schur function. So it acts scalar as a scalar on Schur function, and this scalar is equal to, in fact, our already used this sum over all boxes in the Young diagram, lambda psi of h j minus I. So U as a lambda of p. So maybe it's a bit unfair because of I write very many very unclear definitions and then formulate a very nice theorem which is also very unclear, but in fact it is not very hard to understand it through the boson-fermion correspondence and through the representations of this F of this Fock space. But let me skip this. So I don't know, maybe I just have an idea that maybe we prepare some list of facts which is to prove this theorem, and with necessary effects from boson-fermion correspondence, and to those of you who want to understand this statement and all this boson-fermion correspondence. But now I'll skip it, and we have this theorem for D, and therefore now I can rewrite the expression for function z, for the function z. Rewrite z. So I have this. And what we know already. We know, in fact, one more thing that I have is this old formula for the product of two Schur functions. In fact, we know that yes, know that sum over all lambdas s lambda of p s lambda. Let me write instead of s lambda of p1, p2, etc., just s lambda of p. S lambda of q over h bar is equal to yes, e to the power p I q. Let me write q I p I over I h bar. Yes, I from 1 to infinity. And now, okay, we know this, and how to rewrite this z in terms of operators in the Fock space and this vacuum and co-vacuum vectors. So we know that we already know that this is how d curly d acts, this expression. And so let me write what? Okay, s lambda of p, s lambda of q over h bar. And now what's written? Now what is written here? And I should. Okay. Yes. Now what's written here? This d. Yes, this d is a linear operator in Schur function, and this s lambda, and so this s lambda of q is are constants, and so you may think of this all this expression as a acting this d over on this s lambda times some constant. So you can how to say it. So I mean, I could write this d operator before the summation, so it is just equal to action of this d operator on this linear combination of s lambda of p with the coefficients s lambda of q. Okay. Okay. Do you agree with this step? Yes, no?
Agree. Yes.
Okay. At least Leonid agreed. And then we know that this sum is equal to this sum, this exponent. So it is equal to d of h bar e to the power sum qi over h bar pi over I. And now we remember that this p is so we have this j minus I is an operator of multiplying by p minus I. So I can write it as follows: e to the power sum over qi j minus I over ai h bar acting on 1. Okay, it just I just use the introduced notations. Okay, and so you see that we started with this red formula for the z for the series z, and obtained this blue formula, which is formula for z in terms of operators. These operators in the Fock space of infinite power series in p variables. I recall that this guy means that it's one, just one in this f in this Fock space. So we have this j minus j minus operators which are multiplying by pi, and we obtain this, and then etc etc. Okay.
Okay.
Great. The next step we had like in September generating series H for the simple Hurwitz numbers in order to compute topological recursion differentials omegas. We had this H, this H series. So let me write operator formula for HGN. So again, I want to remind that, for example, for simple Hurwitz numbers, so we had for simple, I'm afraid that Petr Igorevich was right about that time. For simple Hurwitz numbers, HGN dot is equal to sum overall, let me say lambdas, H lambda G, x1 to the power lambda 1, etc., xn to the power lambda n. So it's a sum overall partitions lambda of with n parts such that the corresponding covering, oops, has a genus G. And you remember maybe that we discussed this Riemann-Hurwitz formula, that we can rewrite this Hurwitz numbers h lambda m in terms of h lambda g, and we can collect them in this power series, and this is for all parts lambda 1, lambda 2, etc. They are no ordered here, so it's a sum over all this. It's a symmetric in x variables, and you can write just the same series HGN dot for the generalized double Hurwitz numbers. In fact, let me write Hn is a sum over all G. So Hn depends. This H capital guys depends on X, of course. So Hn depends on X1 is a sum over all J. H bar to the power 2 G minus 2 plus N H G N dot. Yes, and equivalently this HGN this HN is equal to, in fact, sum overall. So let me connect this H to Z. Yes. So in fact, roughly speaking, not formally, but roughly speaking, this H. I hope you understand how this H and this Z are connected. I mean, if you again expand this Z and obtain in front of the monomial of p variables, you obtain some numbers, then you can collect these numbers in this H series. Formally speaking, you can write something like this. You can write sum overall tuples k1 kn dz. So you can differentiate z to extract the coefficient. In fact, you want to extract the coefficient in front of this monomial pk1, etc., pkn, and you want to eliminate all other monomials. So I write here p is equal to 0. So I and x1 to the power k1, etc., xn to the power kn. So it's a formal equality, but I hope you understand what is the meaning of this connection of H and Z. And finally, we know how to rewrite Z in terms of operators on bosonic Fuchs space, and now how to write H in terms of the operator in the Fuchs space. Hn is equal to, in fact, sum overall k1, etc., kn, x1 to the power k1, etc., xn to the power kn. And now what do you see here? You see here differential operators, d over dpk1, etc., d over dpkn. These guys are J. And this operation is in fact what I called co-vacuum in the beginning of the lecture. So I want to write J1, I want to write co-vacuum. This corresponds to this. Then JK1, etc., JKN. It corresponds to these differential operators. And then Z. And then Z. And Z is a D exponent sum qi j minus I over I h bar, I from 1 to infinity, and a vacuum. Okay. Is it right? Do you agree with this formula? In fact, in fact, there is a mistake here, and I want you to try to find this mistake, the mistake. Or just ask something.
При дифференцировании факториалы не вылезают?
Нет, потому что тут как раз все хорошо, потому что здесь, где? Вот здесь сумма по всем наборам. И как раз при дифференцировании как раз так и получается.
Хорошо, да.
Тут как раз очень хорошо подобрано. Но на самом деле ошибка в том, что если посмотреть на определение J, то у меня тут было в определении J еще было умножить на M, M d по dpm, то есть Jm было M d по dpm, so I had Jm M times d over dpm, so I should divide or multiply all these guys to k1, kn. So I should jk is equal to m d over dpm, so I should divide over k1, etc. kn. So, does anyone agree with this formula? So, no one or everyone or... Так, Миша, Полина...
Похоже на правду.
Похоже на правду. Alexei, how are you? Do you hear me well in Vychkov?
Yes, it's okay. And I also agree. I don't see a mistake there.
Okay, cool. And so now we could see the goal. In fact, the goal is to obtain obtain the sum over graphs formula for, in fact, not for H, but for D. No, okay, let me say for H. This is the goal. And how will we proceed? You see, now H, so if you forget about this prefactor, we have this, it calls correlator, but we have this expression this vacuum and co-vacuum. So, and there's some J operators, yes, J, this D, and this again, this sum. And in fact, we know some nice facts. For example, if we have an expression like this, it is equal to 0 because of so like this, yes. If we have an expression like this, it's equal to 0 because of we have 1 times pi and then take a coefficient in front of the free term. And so if we have some summands where J with minuses stay near the co-vacuum, we obtain 0. So if J minuses are on the left, if we have a summand in this huge sum where the J minuses stay in the left of the expression, we obtain this summand is equal to 0. And then at the same time, and maybe let me write anything and anything here. Is equal to 0. And in the same time, at the same time, if we have anything here and J with positive I to the right, then we also have 0 because of J with positive I acts as a differential operators, and here, and this is 1. So we differentiate 1 and obtain 0. And we have we know how these J pluses and J minuses commute to each other because of we know this, the where is it from the seminar, and okay, I can't. So we know the commutation rules. Yes, we know the commutation rules of J operators, and the goal is to commute all J minuses to the left and all J pluses to the right, and we obtain some summands. So we obtain some coefficients, and therefore we will have some non-zero summands, and all other summands will be 0. And in the end, we will have some closed formula in terms of sum over graphs for this H. And why we want to obtain it? Because of afterwards it is more or less so it is convenient to prove topological recursion through this explicit expression. And what we do not know now is how to compute this curly D operators. And now so I want to deal with this curly D operators. So okay, questions? Okay, then let me one more. Yeah, let me introduce one more guy, one more operator. And definition. Epsilon of U and Z is a following sum of these E hat operators. z, yes, z to the power m, sum over k. So all this stuff looks awful, but in fact it's very, very useful, and finally quite nice, I hope. So just a definition, this operator epsilon, but using this, so maybe I should left it for the seminar, this formula, say proposition for the seminar, that how to explicitly write down explicit expression of this big epsilon in terms of J operators. Epsilon of uz is equal to okay, let S is equal to this guy over Z, and then epsilon of uz is equal to 1 over u s of u exponent u s of u I j minus I z to the power minus I e u s of u I j I z to the power I minus 1. It's just more or less immediate corollary of, so proof immediate corollary of the definition of E operators of this, say, of star definition. But let's deal with this in the seminar. Okay, we have this epsilon operator, and one more, and okay, how to deal with this D? So we know how to compute J, but how to deal with D? For this, let me define the following guy. So let me define G bold. G bold M is equal to so conjugation of J by D. Gm D of H. So who is a D inverse? So it's an operator inverse to the operator D. Okay, and then it is nice how we can rewrite this formula for H. In fact, we have here JD, and as usual, we can insert here between each pairs of J, we can insert D minus 1, yes, and therefore we obtain what will we obtain? we obtain something like this: hn bullet x1 etc. xn is equal to sum overall case x1 xn over k1 kn. Then we have this d minus 1, and then j bold k1. Do you agree? jkn, and then this exponent. Do you agree? It's just
саму формулу, чтобы мы сравнили.
Что?
Ну, покажите саму формулу, которая сверху, чтобы мы сравнили непосредственно.
Давайте, да, потому что я понял, что в некотором смысле на iDraw писать удобнее, потому что там каждый может промотать, да, тут нет. Давайте я ее скопирую просто. Ну вот, да.
Ну вот кажется, что нужно умножать не на d в минус 1, а на d, чтобы сократилось слева от g.
Почему? Я вот сюда, вот сюда записываю d в минус 1 d, в минус 1 d.
Ну и вот у нас из j красивого возникает слева d в минус 1, а мы хотим убить его d. А вы написали d в минус 1.
Согласен. Из этого j жирного возникает d в минус 1. Да, тут надо написать d. Угу.
Ну, теперь я согласен.
Так, хорошо. Остальные, кто-нибудь еще согласен? Okay. I hope that you agree. And okay, then the next is I claim that this D also so what I want to say that how to okay, maybe let me left it this way. The next, okay, let me left it in this way. And then the next proposition, the next step is to obtain the explicit formula for this G, bold G. So the first proposition for the seminar is the explicit formula for this epsilon, and the proposition 2 also for the seminar. Proposition 2 is the following, that this J bold is equal to the following. So it's sum d over okay, d dm of y over dy d r times substituting y is equal to 0, u to the power r, z to the power m, and then let me write epsilon. Yes, let me write this epsilon of u h z. So this epsilon is epsilon from proposition 1. So it is this expression. And this phi function. Okay, and this phi function defines as follows. So phi 0 where phi 0 of y is equal to 1 and phi m of y is equal to exp of sum of psi of y plus So this guy. Let me maybe write some example. For example, I don't know, phi 1 of y is equal to what? Is equal to just, so exponent, m is equal to 1, so it's a 1 summoned, psi, again m is equal to 1, I also is equal to 1, so it's, here we have 2 minus 1, so it's 0, so it's just exp of psi of y. Or for example phi 2, where psi again is this formal power series in the definition of z, or which are connects to the Horvitz numbers. So this phi 2 is equal to exp of okay, m is equal to, so we have 2 summoned in fact, psi of y 2 minus 3, yes, minus h bar over 2, plus psi of y is equal to 2, 4 minus plus, yes, plus h bar over 2. Okay, so and etc. And also for, do we need this f5 for m less than 0? I think no. So yes, this is okay, and this is the proposition for the seminar. And so finally, what we have, finally we have the following. So we have that we can now Okay, let me define one more notation. So again, definition. Okay, maybe let me pause a bit. Any questions for? So what we have now? So what we had? We had that. Then we introduce many definitions of these strange J, D operators, etc., etc. Then we rewrite this Z where in terms of operators in the bosonic Fock space. Then we recall who are these H and rewrite this H in terms of the bosonic operators, and we obtain this important formula for us. And then we discussed I discussed the idea of what we are going to do, and now I'm trying to follow the plan. But in fact, I left a lot of exercises for the seminar. So I left this for the seminar and expression for this epsilon for the seminar. So why do we need this expression for epsilon? Because of later we express J bold in terms of these epsilon operators. Yes, so we have this explicit formula for the epsilons, and therefore we have this and therefore this statement gives the explicit formula for J operators. So my claim that I'm following the plan, I'm to somehow to write these expression in terms of J operator, J minus and J plus operators, and now I want to compute them to eliminate this vacuum and co-vacuum. So now I conjugate D operator because of in this expression in this expression I know everything in terms of J operators except of D, and therefore I conjugate this D, and it happens that this J bold I know how to write in terms of J operators. It is written here. And sorry, now definition, the next definition to be able to write formula for H is follows I hope the last one maybe. That let me define U plus. So it is an operator. So not an operator. It's a transformation that takes a Laurent series F small to the series in say U and Z variable. Let me write F at U Z. So U plus takes F of UZ and maps to series in X variable. Maps to series in X variable. So U plus action of non-F, it's a series in X variable. So E is equal to sum over all M, x to the power M over M. So it's a formal power series in X. And here sum over all R, d phi m dr over dy r y is equal to 0. So you see this is this part from this previous proposition. And what is this? This means that taking the coefficient in front of the monomial u to the power r z to the power m in all what is written to the right. So in this epsilon. Peter, could you meet Maxim? And so here I write something like us of uh z d over dz y of z s of and any series f u z. So this is the definition of u, this transformation u. I hope that it will so it will be more, it will be nicer than we will deal with this a bit. Now it's maybe a bit awful, again some strange e to the power us of z d over dz, etc. But let me now define it as it is, and I hope on the seminar and next time it will be better. And the finally theorem, maybe let me write down the theorem that which we prove next time. Theorem that hn of hn, yes, in now in z variables, not in x variables, but in z variables, and without bullet, so it's a series for connected numbers, is equal to un plus etc u1 plus. Here this coefficient means that maybe I should write here, say I, and then zi, and zi. So I mean that we have n such operators, and we these operators acting on the following guys. So it's a sum over all simple graphs on n vertices, and WKL minus 1. This is the weight of the edge, and this weight of the edge WKL is equal to more or less this huge exponent. WKL is equal to e to the power h uk ul s of uk h zk d over dzk, and the same for L, S ul h zl d over dzl, zk zl over. So it doesn't matter. I could just write wkl zk minus zl squared and minus 1. Okay. So I think I should stop now. And any questions? And I hope that you see the goal now, and I hope that you more or less understand the steps, today's steps. But anyway, we prove this theorem next time, and we hopefully prove these propositions 1 and 2 now on the seminar. So questions? Yes.
Well, all these operators that or definitions that are introduced, there is some intuitions behind, or it's like this because it works.
So we have intuition for Z, the series Z. We have intuition for series H. This important expression. We do not have any intuition behind this expression. It's just a formal expression in terms of these J and D operators.
So basically, the D is ketangent more or less, or what?
Yes.
D,
yeah.
D
yeah.
is more or less a ketangent.
Yeah. So we have an intuition of all this. So I would say that you're right that case by case, for simple Hurwitz numbers, for example, you also can deduce this formula from the cut and join operator, yes, for example. But if you know, say, boson-Fermat correspondence, then maybe the picture will be more colorful.
What he said, I think it's right. It's for simple Hurwitz numbers, for instance, it's indeed just precisely the cut and join.
Yeah. But yeah.
Well, another second question. So, we have this boson-Fermat correspondence, and there are also some. So here, basically, it's for GL infinity, and there are some other algebras. We have also these pictures where you can play this way, or it's less known.
So could you?
So basically, here we have a lot of good notations, complicated or not. And all this is for the GL infinity hat, basically.
Yeah, all these guys from, in fact, formally speaking, from the GL infinity hat. Yeah.
Now you have some other algebra like B infinity and all these smaller or bigger algebras. Do we have also some good expression like this, or is?
In fact, I don't. So in fact, I don't know. So there are also expression for your not-oriented Hurwitz numbers in terms of skew, maybe Schur function, or some, how it calls.
It's basically Jack polynomials.
Yeah, Jack polynomials. And it also has some representation, meaning of some representation of some algebras, but I don't know.
Okay. Thank you.
Yeah, so more questions? Еще вопросы? Ну хорошо. Тогда давайте оставим вопросы до семинара. Да, семинар через полчаса, да, в 3, как обычно в итоге, в общем. И тогда я останавливаюсь.